Let's consider a data structure with a particular set of requirements. It has to be able to be traversed in sorted order reasonably quickly. It has to be able to insert and remove elements reasonably quickly. And it has to be fast to search for a particular element. The most intuitive solution one might immediately come up with is to have a linked list which is sorted upon insertion. What I mean by this is that when you modify the add step of this linked list, instead of inserting to the start or the end of the list, you traverse to the right place in the list and you insert there. For example, we have a linked list of integers which goes 1, 2, 4, 5, 6. We need to insert the number 3. We go 1 is too small, 2 is too small, 4 is too big, that's where 3 goes, before the 4 and after the 2. Makes sense? It's sorted at all times, we always have it sorted. To search, we just traverse through until we find the right number because it's sorted. We know that if it's if it's going to be larger than the first number, it's going to be further along the list. If the number is larger in the list and it's not there, it could work, but it doesn't seem that fast once it gets really big. Let's take one that's 1,000 length. We have to search quite far through that 1,000 length list to get anywhere. And that might not be optimal. Maybe there's something more efficient we could do. This is when we have to consider the use of our references, our pointers in these nodes, and what we could do with them. Do we just have to have one, or can we have multiple? And can we make some rules about where these pointers point to, which will help us in this endeavor? Well, what if we made our rules such that they helped us traverse this list in the most optimal possible way? And what if we just had a more helpful number of these references? Let's say that our nodes can point to 2 items. And let's make the rule that one of the items is less and one of the items is greater. You'll see very quickly how this can be useful. Let's start off with just one node at the top here. This node will have a value of 5. And let's say that the left node is less and the right node is bigger. So since the left node is less, we want to insert 3. We start with 5. 3 is less than 5, it goes to the left. Make sense? Simple. If the right is larger and we want to insert something to the right, let's say we're inserting 7, and now we have 7 to the right. So it goes 5 and then 7 if you try to find the largest element. To find the largest, you just go right, 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 right. Find the smallest, you just go left, 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 left. It's quite simple to find the largest and the smallest. But you might be wondering, what if I have a number that's larger than 5, but smaller than 7? It has to go to the right of 5, but then what does it do? Well, just keep in mind that this is a recursive sort of data structure. Every node has these 2 references. So we go 5, well, 6 is larger than 5, goes to the right. 6 is smaller than 7, so it has to go to the left of 7. So it goes 5, 7, and then to the left of 7 is 6. But now you might be wondering how we can make a useful traversal out of this. How do we get this into sorted order? Well, the sorted order question actually becomes a lot simpler if we consider how our recursion is done. We can traverse the list. It's not actually a list, it's nonlinear anymore. We can't really call it a list. We can traverse our nonlinear data structure, our tree, in such a way that we get into sort order by going left, center, right, or right, center, left. The way we can do this is we can follow through. Let's say we want to go largest to smallest, because that's where our tree right now is a little bit more complicated. It's a bit of a better example. We go to the rightmost, rightmost, rightmost node to get the largest for the start. And then what is the second largest? Well, the second largest is going to be what was the center of the subtree that the largest is in. What does that mean? Well, remember, this data structure is recursive, so every node can be considered the root of its own subtree. Let's visualize the subtree of just the system with the largest node. That subtree has its center node, its lesser node, and its greater node. But what do we know about the subtree? We know that every one of the nodes in this subtree is greater than the nodes above it, because it was on the right of the node above it. So we know that it must have been larger. Since we know that it must have been larger, we can say that it is indeed all larger. We just have to traverse this subtree in order. And to traverse this subtree in order, we go furthest to the right, then we go to the center, then we go to the left. And remember, when I say in order, I mean largest to smallest. So right, center, left is the in-order version of that subtree. And then we go through every other one of the subtrees, and we go right, center, left, right, center, left, right, center, left, until we get through the whole tree and we get it in the correct order. We go left, center, right if we want the opposite order of that. So if we want smallest to largest, we just go all the way to the left to get the smallest, then center, then right, left, center, right, left, center, right, left, center, right, and we get the smallest to the largest. How do we search? Well, at every step, we simply ask ourselves the question: is the one we're searching for less than or greater than the current node? So if we want to have another binary tree, let's say this one has a root of 0. And then, well, we know that negatives are going to be on one side and positives on the other. That way we can say, is our number negative or positive for the start? And let's say on one side we got -5, on the other side we got +5. Right? That's what our tree looks like right now. And I'm deliberately only telling us about the nodes we can see. We can only see the root, the left, and the right. That's all we need to see. Because we don't care about what's on the rest of the tree. That could be really large, really small. We don't care. We just care about what we're searching for. And let's say the number we're searching for is -3. So we go 0. Is it -3 positive or is it a negative? Well, it's a negative. So we can go, okay, it's towards the side of -5. But it's larger than -5. So it's got to be to the right of -5. So we go center, then we go left, then we go right. And what's the right of -5? Well, in this case, it was indeed -3. And then this sorting algorithm, the searching algorithm, I mean, can be applied across the board. To search through the tree, all we need to do is just ask ourselves, is it less than or greater than at every step? And if it's equal, that is a separate case, but it's not much different. We just have to set a condition that one of them also takes in the equal. So one of the sides is less than or equal to, one of the sides is greater than or equal to. So hopefully this made binary trees a little bit more clear and understandable for you guys. Good luck. Hopefully it helps with your coding. The tutorials do cover the coding implementation of a binary tree, and hopefully that'll be useful to you. Thank you so much for watching. Enjoy your day.